In this video, we're going to look at intervals and delta balls. These are very easy concepts, but they're also very important concepts, and it's important to have a visual idea of what they are as well as a symbolic idea of what they are. The idea behind intervals are something that you've been introduced to in high school. An open interval, which is usually denoted as a and b inside parentheses, is the set of real numbers such that a is less than x and x is less than b. And it is traditional to draw this on a number line in one of two fashions. In high school, you learned how to draw this by putting an open dot at A and an open dot at B, and then shading the part of the number line between them. And that was the open interval between A and B. In real analysis, we tend to replace these open circles with just parentheses. We're mimicking the notation up here. And so that gets labeled as A and B. And if we want to, we can shade the inside here. And that again is the open interval between A and B. Closed intervals work the same way, except that they include their endpoints. So a closed interval is usually denoted as A and B inside square brackets, and this is the set of all real numbers such that A is less than or equal to X and X is less than or equal to B. And on a number line, there again are two ways of denoting this. In high school, you learned to put big closed or solid dots on the two endpoints and then shaded the stuff in between. And in real analysis, it is traditional to just put square brackets like that, and if you want to shade the interval. In real analysis, it's often the case where we don't bother shading the interval, particularly if it's getting in our way. So you'll sometimes see an open interval simply denoted with the parentheses around its endpoints like this, and a closed interval denoted on the number line by simply putting the endpoints like this. So we don't always make a point of shading the interval. Now, the special thing about open intervals is that they have a particularly nice property. If we look at a number line and we draw an open interval on this particular number line, so I'm going to let S be the open interval between A and B, and if X belongs to S, no matter where it is, there is always space between X and the two endpoints of the interval. And that fact that there's always space between X and the endpoints of this open interval means that in an open interval, so if I have an open interval, and if this open interval contains X, then there exists a delta bigger than 0 such that the open interval, and I need to clean my notation up there just a little bit, the open interval x minus delta to x plus delta will be a proper subset of the open interval. And just to draw this in a different color, what we would be looking at would be a little delta interval like this, where this endpoint is x minus delta and this one is x plus delta, and this little distance in here, that distance is equal to delta, as is this distance. And I want to kind of just blow that chunk up. What we're looking at on that chunk is this sort of an idea. There's my number line, and here's A, and here is x minus delta, and here is x, and here is x plus delta. And way out here somewhere is B. What I want to notice is that delta is this distance, delta is this distance, and this is the center of this particular set. And the notation that is often used to denote this kind of a balanced open interval is called a delta ball. So we call the open interval x minus delta to x plus delta, an open delta ball centered at x. Sometimes we just call it a delta ball. The delta is considered the radius of this ball. And because this is kind of awkward notation, it takes a lot of room, we usually write b of x comma delta for the set x minus delta to x plus delta. And we usually read b of x comma delta. This is usually read as the delta ball centered at x, or it can be read as the ball centered at x of radius delta. But most people will just shorten it to the delta ball centered at x. And so the important fact that we have about open intervals can be stated as follows. If x belongs to an open interval, then there exists a delta bigger than 0 such that the delta ball centered at x will be a proper subset of the interval. Now, closed intervals do not have this property. So closed intervals don't have this property. And it's very easy to illustrate why. Let's just draw a number line. So here's my number line, and let's draw a closed interval. So there's my closed interval, and I'm going to make the note that A itself belongs to that closed interval. And now let's look at delta balls centered at A. So if I start to look at a delta ball centered at A, that red set is going to be a delta ball centered at A. And you'll notice that every delta ball centered at A contains points out here. So every delta ball centered at A contains stuff over here. And that's enough to say that this delta ball cannot be a subset of the closed interval from A to B.